Alright everybody, so it's time for part 3 of Leibniz notation and rates of change. It's two topics that I'm lumping all together for this video series and the assignment that goes with it. So I think with, this is my opinion, but I think with some of this stuff, it would help to hear it more than once, alright? I think for most people, the further you go in math, you'll get to a point where it takes time for everything to sink in, all right? Maybe you're breezing through this and you feel like a genius, and that's great, but at some point, it will get there where you need to hear it, think about it, hear it again, think about it again, and just have it slowly sink in, and then one day you'll realize that you understand it, okay? So I'm going to remind you of some things. Okay, so in this video, partially it will be a reminder. There will be some new things in it. I might repeat some things that I talked about in earlier videos, but in a different way. So if you didn't get it with my other examples, you have a fresh shot at understanding it here. Okay, so suppose that y is a function of x. And all that means is that there's some formula where you plug x in and you get y back out. Okay, then delta y over delta x, which is something that we calculated in previous videos, that's called the average rate of change of y with respect to x. The delta means change. It's like we measured the changes in y and x and we divide them. That's what that is, all right? dy over dx is the derivative for those that are into brevity, all right? Or you could say the derivative of y with respect to x. Sometimes it's said that way. Or the instantaneous rate of change of y with respect to x. Alright, these look similar, don't they? There are new notation. This is what Leibniz notation is. It's writing the derivative this way. It looks kind of like that. Is that a coincidence? Why does this new symbol for the derivative look kind of like that delta notation? And the reason is that if the changes are small, so for example, if delta x, if the change in x is small, now how small? Well, it might vary from problem to problem. But if delta x is suitably small, then the derivative will roughly be equal to delta y over delta x. Or what is delta y over delta x? The actual measured changes of the variables, okay? So that's why we'll use this notation for the derivative sometimes, because we want to study changes, and it does match up with, our other symbols we use for changes in variables. You see the delta notation even in science class, like if you take chemistry class or physics class, delta is still used in those classes to mean change. It's universally accepted use of that symbol, that triangle, the Greek letter delta. Okay, so now both of these are rates of change, right? This is an average rate of change, and the derivative is an instantaneous rate of change, all right? But we should think about this. Should think about what is a rate of change. And why do we calculate delta y over delta x? Why not just calculate delta y or just calculate delta x? Why do we calculate them together? So I want to answer all those questions with one example, all right? The short answer is because we normally, maybe not all the time, but normally we want to see how the variables are changing together, all right? Or what I mean by that is how change in x might influence change in the other variable y. And here I'm just using x and y in totally generically. Not all variables are x and y. You might use different letters of the alphabet to represent different variables. So let's think about an example. So suppose that we have a moving object and there are two things that are changing together, all right, for a moving object: position and time. Okay, you can agree about that. That's what happens when something moves. All right. So I got my car and I'm driving on the road and it's moving, and then we contract the position and the time. So just think about that. And I can, it's possible. You might not understand how this is possible, but maybe a radar instrument can record some measurements about position and time. In fact, I went to electrical engineering school, and I still like to make circuits. And I have this thing which measures, I can make a circuit and write a program for this thing, and it could measure the position of something that's moving at a given time, all right? So it could, this does it with sound waves. But we could use like a radar instrument or a laser instrument. So this is entirely possible that if something is moving, we could record information about position and time. So those are the two variables that are changing together, all right? So think about it. If I just track the position, that wouldn't tell you a whole lot. And if I just track the time, that wouldn't tell you a whole lot. But what if I track them together? Okay, so suppose my little measuring instrument and circuit that I make and computer program that I write, suppose that I record these measurements, okay? At time t is equal to 0, we'll just make that the time of our initial measurement. The position s in miles on the road is 0. So in the beginning, we'll say you're at time 0 and position 0. And then at time 0.0015 hours later, okay, so that's not a lot of time that passed, right? Then you've moved what? 9/100ths of a mile, okay? So it took you 0.0015 hours to move 9/100ths of a mile. That's what our radar instrument recorded, okay? So suppose that we took those measurements of time and position, and we calculated delta S over delta T. Literally, that means how much did your position change and how much time elapsed, or how much time changed, okay? So say you do that. How are you going to interpret that number? Well, all right, I'll do this and do that. And if I divide those, if I divide that number and that number, the number I get 60, but my units are miles over hours. So you see how the position and time are changing together. We want to measure them both and see how they change together, because it gives us a number that we're interested in. That's the average rate of change, but I guess you could also call that the speed. And, we might sometimes want to know how fast something's moving, okay? So that's what a rate of change is, okay? A rate is a quotient between two different kinds of numbers, like miles and hours. Okay, so that's what a rate is. And then obviously there's change happening. The position's changing as you move, the time passes, and so on. So that's why we call it a rate of change. Now, so I could say this in addition. See how that change there is pretty small? I think it'd be a safe assumption that the derivative, ds over dt, the derivative of position with respect to time, would be about 60 miles an hour. All right, that's the instantaneous rate of change. Okay, so the deltas are the average, the derivative is the instantaneous. And so I feel like even though there's no formula here, it's safe to believe that that derivative is about 60 miles an hour. Okay, all right, so hopefully that will give you a context to think about all the words we use when we say rate of change, when we say the derivative or the deltas or so on. Like, you can think about it like this, okay? And if you ever take physics class in the laboratory, you might use something a lot like this to do some experiments where you make measurements a lot like I have here, all right? Okay, so let's talk about one additional way that we use Leibniz notation. This will be new. This will be something I didn't cover in the other videos, but the notation is used this way, okay? And I think, probably if you're in this class, you need to learn how to read some math, okay? Like here, so I just, I keep some books on my bookshelf, and here's an old book on mechanical vibrations. So my grandfather, let's see, there it is, Warren J. Brignac. So he was a mechanical engineer, and I have a lot of his books. And we're going to have to learn to read some math, okay? When you see all these symbols, does it look intimidating? Well, we need to try to get you to the point where it's not intimidating. So when you move on to something else besides math, and you take a science or engineering class and you see all this math everywhere, well, you know, we don't want you to be afraid of it. So very gradually we're going to, you know, teach you more and more notation, because there were some words in that book, I understand that, but there's also some notation, okay? Now you're like, this is an old book, all right, and you might say, oh, like, what, is that really still accurate? And I can say, yes, if you got a modern day book on mechanical vibrations, it would still look a lot like what you saw in there. But it is an old book. When my grandfather was considering coming to Texas and working at General Dynamics, used to be, that's what it used to be called. Now it's Lockheed Martin. He was touring the facility, and one of the selling points they gave him was that it had air conditioning there, and he could wear the same shirt every day. That's actually what they told him, because having air conditioning in the workspace was not common at the time that he was considering working there. All right, so they had air conditioning. He didn't get all sweaty, and apparently they told him he could wear the same shirt to work every day. Anyway, so why am I getting off topic? I just was thinking about that story the other day, and I guess I decided to tell it. Anyway, so here's some, what were we doing? Notation. Okay, so notation. So for this function, y is x to the 5th power, we could say y prime is 5x to the 4th power. Yeah, we could say that's the derivative. We've talked about the rules. We could say with Leibniz notation that dy over dx is 5x to the 4th power. You might read that as the derivative of y with respect to x. But we also use Leibniz notation like this. This says the derivative with respect to x of x to the 5th power is 5x to the 4th power. Sometimes we write like that so we don't have to write the function separately, okay? And it's just understood that, you know, if I say the derivative with respect to x, x is the variable in that formula, okay? Another example, suppose there's a function a is 4b squared plus 1. A is a function of b. We could say a prime was 8b by the rules. We could say the derivative of a with respect to b is 8b. Same thing, that's just Leibniz notation. Or we could say the derivative with respect to b of 4b squared plus 1 is 8b. So there are all different ways of saying the same thing, but that's the way math is. There are lots, you'll find that no matter what you're doing, there are lots of ways to say the same thing. But when I look at this, I say, well, that's the derivative of this with respect to b. Then, you know, b is the variable over here. All right, in that formula, b is the independent variable. And this is the derivative of that with respect to b. All right, well, let's do a few examples of using Leibniz notation like that. Then I think that we'll be probably all done with Leibniz notation. So here's, it says, evaluate the following given that k is a constant. Let's see, so the derivative with respect to u of 3k squared plus k to the 4th plus u squared. Okay, so up here it says k is a constant. All right, so it's some unspecified constant, but it is a constant. And when I look at this, I say, well, that means this is the derivative with respect to u. That means u is the variable over here. All right, well, that's okay. U squared, u's the variable. So, well, let's see. 3k squared, that's going to be a constant, right? Okay. And then plus, what's the derivative of k to the 4th power? Well, k is a constant, so is k to the 4th power. All right, plus derivative of u squared. Now, u is the variable. So 2u for u squared, 2u. So the derivative with respect to u of 3k squared plus k to the 4th plus u squared is just going to be 2u. All right, so you will see Leibniz notation used that way. You'll see it used like this too. What's the derivative with respect to t of k times t minus 1? Well, okay, t's the variable here, k is a constant. It would be just k, all right? And that goes back to our rules. All right, why is that? Well, because, like, for example, y is 3x minus 1. That is a line that has a slope equal to 3. Therefore, y prime is 3. That's normally how I explain that one. All right. The derivative, one thing it can tell you is the slope of a curve. The curve y is 3x minus 1 is actually a line that has a slope of 3 everywhere. So y prime is just 3. So here I see this one like that. K times t minus 1. That's t to the first power. It's like 3 times x to the first power minus 1. All right. K is a constant, so you could see that that's the slope if this was a line. And that's the way that it's going to be. Okay. I think I even included a rule once that in one of my earlier videos that if y equals mx plus b, okay, where m and b are constants, y prime is m, because m is the slope and b is the y-intercept. The derivative tells you the slope of that thing, okay? All right, so we could accept this as a rule, and that's really what I'm thinking about when I'm looking at that one.